So welcome to the sixth lecture of this course. This is a crash course in quantum processing. Last time we talked about the nice features of entanglement and how our quantum mechanics is truly affected when we introduce the concept of entanglement. Today I will talk about the system environment model. This is a nice model that we begin with in order to understand what happens in quantum information theory part of this course. So let's start out by saying that we have some basis states, some important quantum states that we can begin with, like the phi, like the psi's, and qubits, for example. And we have also nice gates, nice operations that we can perform in our qubits or our wave functions. And we said this kind of unitary. We did not talk about non-unitary transformation, but here the unitary transformation is the predominant and most important part of this. We have the X NOT gate, quantum NOT gate. We have the Z. When you start to flip here, X, you flip. The Z, you start to flip the sign. And sometimes you can map from 1 to -1 and from plus to minus, so you just change the sign. For Hadamard transformation, Hadamard gate, one of the nice gates we will see quite often in this course, that you map or just transform a 0 to plus, maybe 1 to minus, and nice things like that. Another feature here is the measurement. We can do some measurements if you'd like to get the probability outcome of a measurement of the this M, of this projector M, and you can apply the the sandwiching the wave function with this nice operator, this nice M operator, and this is actually before you get you do the measurement. So you expect this probability outcome before you do the measurement. And once you do the measurement, you start to evolve the wave function and see this is a nice shape of the wave function after performing the measurement. So another factor here is the composite state, and those are the ones that we will see a lot from now on. That we have tensor product states that are expanding our state space or expanding our Hilbert space, and you can see that they scale with the number of strings that you have. For example, if you have tensor product for zeros or ones, you have four-dimensional Hilbert space, because and now you have two states. This is number of states, and these are number of basis vectors that you have. Also for statistical, or maybe just say a statistical combination, or this for density matrix, that you have all the time stochastic combination of the density matrix for specific probability, that maybe we have 50-50 for psi I, and also for psi j. Okay. And this is how we can construct a density matrix and a statistical combination of both with definite probability that we have here. So let's take an example for this system environment model, that now we have a wave function. Now we have a qubit, for example, psi, and we have the environment. This is for the environment. And now we transform that, and we do some unitary transformation over the system for environment and the wave function, or environment and the system. And then we expect that after measurement that we see this kind of all orthonormal basis for our environment that we expect. And now we would like to know what happens to the wave function, to the state itself. So the legal mapping that we do is that we try to relate the input density matrix of this system to the output density matrix of this system. So the unitary transformation that happens to the wave function, to the evolution of this wave function that the environment affects, or even plays a role in transforming this wave function by this kind of transformation that we have here. So if I would like to write down this stochastic combination of wave functions that we have here, so we can sum for all measurement for all the environments. So I can write that for all orthonormal bases that I have. So for example, I can write this like that. Let me draw it here. For wave function, but I will say that this is or this is for this XOR. So I have this kind of wave function, or this one, or this one, or this one. So it can be expanded like that. Okay. And so on until n. So this is, if you look at this kind of term here, this is known as cross operator. This is for Karl Kraus, German theoretical physicist. This is very known operator that you have. This is a quantum operator that's what's sometimes called error operator. It's named for Kraus, and it's called En or Ek, whatever. So we just changed the notation here because I expanded for n. And the output density matrix that I have here can be written as just this quantum operator as a sum for all n, okay, for this cross operator with its conjugate again here, that the system or the cross operator affects the input state. This is input state, okay? You can make sure for yourself and check that if I sum for all n for this cross operator conjugate with itself here, you find it's equivalent to the identity matrix. So let's make sure that we fully recover this. Take few seconds to think of this, and did you get it right? Okay, so if you look here, you can sandwich because this is conjugate, so it would be like this. N. Okay, so this right, and with the wave function, no function here. So, okay, this forms an orthonormal basis set. This is identity matrix actually. So if you look here, you'll find that this is equivalent to the identity matrix. Let me tell you that this operator, this cross operator, it's not necessarily unique, because sometimes you, because you sum for all basis states for all measurement outcomes that you have in your output density matrix. So it's not necessarily unique because we are getting over many measurements or many measurement outcomes. So let's try to say something about the validity of the quantum operation here. So the quantum operation here is legal mapping the density matrix, the input density matrix, to the output density matrix. So this is actually E5 or E0. It can be a legal one when you try to say the following. There's four important characteristics here. That the trace is trace preserving, the trace is equal to 1. Okay, the trace of the input, the output density matrix is equal to 1. And if you, this is E, I'm sorry, this is just E. If you sum for all n for this probability, I forgot here the probability, for our density matrix is equivalent to also the sum for this kind of quantum operation. So this induces the fact that we have linearity in our quantum worlds. And you will find also that this is kind of trace preserving, since have to be equal together if you would like to make the sum for this operation. Okay, so another one here, this forms an important positivity of your system, and we actually exposed that before, when we introduced the density matrix operator or density operator. Another one here that forms what we call the complete positivity, that regardless of the references that you have in your system, that if you would like to say that you do some mapping, and this mapping is operated in the specific part of the system regardless of the other references, is still larger than or equal to 1. So this is what we call the complete positivity. Okay, and by that we can say that now we have a map which is a valid quantum operation, that we transform the system with the environment, system environment, to measurement outcome that you would like to measure, would like to see. Next time it will be more advanced than this, that we will build this systems or this basics to understand what we call the operator sum representation, which is very important milestone for the quantum error correction procedures. Thanks a lot for watching, and see you in the next time.